If I look at the first example here, it is, let me, if I look at this example here, I'm combining a hydrogen atom with 1 valence electrons, oxygen 6 group, 6 valence electrons, 6, this is 1, this is 6, and this is 1. I'm making H2O, something looks like this or like this. So we are sharing the electron here from oxygen and from hydrogen are shared. That's here. Here in this one here. So those electrons are shared. Those electrons are shared. So we can write it this way or this way. I prefer, my preference is this way because I will have more, but in my mind, this is single bond here, single bond here. That's, I know that's being shared between oxygen and hydrogen. So what type of compound is this? What type of compounds? Ionic or covalent? Covalent. This is covalent. Why? Because both elements are non-metals. Oxygen is non-metal. Hydrogen is non-metal. The other hydrogen, of course, non-metal. So the combination of non-metals yield covalent compound. If I have a metal, there will be no sharing. There, you can see they are sharing their valence electrons. The metal does not share. The metal donates valence electrons. It's a valence electron donor. It gives away, generous, very generous. And the anion, the non-metal, is acceptor. Is accepting those valence electrons, correct? So we have here in this example, let me just take it out. This one here, you look at this. This one is single bond, single covalent bond, and sometimes called what? Called sigma. S-I-G-M-A. By the way, sigma, whether it's in English, I think, or German, sigma means, in German, it means curse. Something very curse, something, you know, evil, very evil, sigma. But when we say in chemistry sigma, does that mean evil thing? It means just sharing valence electron between the non-metals. That's what we mean. The other one, the double bond, it has a name, and the name called pi, capital P, small I. Pi, correct? And it has, this is, you know, the pi from the math, you know, the pi from the math. So this is called what? Double bond, or called bi bond. Bi bond, like single bond called sigma bond, has nothing to do with the word sigma, totally different meaning, but sigma means single bond. Bi bond means double bond. The triple bond has no abbreviation, but they say just triple bond. So you can see the covalent compound, the covalent bonding can have single, can have double, can have triple. Now, do we have a quadruple? No, there is no quadruple bond you have ever seen. But there are called coordination bond, which can be 4, 5, 6, 12. But it's not sharing though. It's not sharing. It's filling the vacancy of loop inside the orbitals. That's totally different. So we in covalent compounds we have single, double, and triple. We don't have a quadruple. There is no covalent bond, quadruple bond. There is none. There is a feature if you want to go further in chemistry and physics. There is called coordination bond, which is there is a loop and then some some donating covalent can donate inside this loop of the orbital itself. So those are, can be quadruple, can be even higher than that. So let's look at something else here. Let's look at the length. Now, what do you think here? Just I want you to think about a bond. A longer bond, single bond is too long, correct? Like this. Carbons here and the carbons here, or whatever the compound, non-metals here, the non-metals here. The double bond, see here, one is here, one here. Now it's a little bit, they come closer. The triple bond, this distance between them. So which we think will be very easy to break, the small one, or the longer one, or in the medium one? Which one? The longer one will be easy to break, correct? Try this one here if you have seen the mall here. If you go to the mall, the area here, the Indian mall, they sometimes sell sugar cane, huge, real sugar cane, long, very long. If you take it, very long, if you take it from the sides, one side you and one side your friend, try to break it will be easy, correct? Now, if you take small portion of it, to break it, what will happen? Difficult, correct? So the longer the distance, the smaller amount of energy you need to break any object, any object. And this is the same thing here for the bonding. So single bond is easy to break. Double bond is moderate. Triple bond is very, very difficult. Very triple bond because they are so close to each other. The electrostatic interaction between the atoms is so gross. I mean, so big, and you cannot rotate. So the single bond far away from each other, you can rotate them very easy. So they can spin like this, or the opposite, clockwise or opposite, counterclockwise. But the triple bond, you cannot rotate it. It's absolutely, you cannot rotate those. And the double bond, even you cannot rotate it, but moderate. But the triple bonds always is difficult. It's not, you cannot break it and you cannot rotate it. So they are not, it's not easy to rotate. Now, if you look at this, let me go here and look. Guys, look at this single bond, correct? See how much energy I need? That's the length. That's the length. You see the length? 154. The double bond is 133. Less. The triple bond, 120, the least. Now with nitrogen, this is the amount, the length, and the length. And if you look at the energies here, so the triple bond here, correct? How much you need? Here the bond length is here, correct? So the bond length is here, which is 120. But look at the energy is where? It's here. Can you see the energy here? The double bond is here. And the energy you need is here. Single bond is here. Just, I mean, just qualitative, so you don't have to. And you have here. So the amount of energy needed to break those bonds depends on the degree and the type of the bond itself. The triple bond, you need a lot of energy, and there's over 100, you know, the bond energy over 100 kilojoules per mole. So over 100. And single bond, you need less than 400 kilojoules. So almost double amount of energy you need to break and form the bond here. And here is just the conclusion here. That's the length. The longer that the bond is, like single bond, the less energy you need. The shorter the bond is, then you need a lot of energy to break this bond. So this is just concept-wise. I saw those type of concepts appearing in multiple choices in the final exam. Sometimes we'll give you sort not false or true, false or true or false, but it give you some side concept. It is very difficult to break and then blank, break, blank, and then bond, then sigma or bi or single or double or triple bond. Then you can just, for multiple choices, it's very hard to break. Triple bond is very hard to break. So here it is. Now we are switching to something new topic called, we talked about electroaffinity, correct? And we'll talk now electronegativity. What is the difference between electronegativity and electroaffinity? So this is very important to know the difference between them. Electronegativity and electroaffinity. Well, when I speak about electroaffinity, I speak about one atom by itself, the gaseous phase, non-metal, like to take in valence electron from adjacent atoms. Electronegativity is the same thing, but you have to have a chemical compound. Within a chemical compound, one more electronegative atom means one atom tries to pull out this electron from adjacent chemical compounds, or from itself neighboring atoms within the chemical compound. You see the difference? Electroaffinity by itself. So it does not take it from by itself as a compound or whatever. But electron and electronegativity is between bonding atoms within the compound, within a compound, correct? So that's the difference between them. Electroaffinity by the atoms by themselves, but this one here, electronegativity by bonding, by compound, within the compound itself. So, therefore, you can see here, even give you the covalent character decreases, ionic character increases. This is what we have last time with the last chapter. We said about the stuff I went through together, and you will see that electroaffinity. Let me go here. Electroaffinity will go from left to right. So let me here from left to right. So electroaffinity and electronegativity. From left, this is left. This is within period, left. This is right. Periodic table. This is an increase. Okay, guys. This is an increase. Well, I'll just write it all up. This is an increase. I'm writing with the mouse. Can you believe yourself, guys? The touch screen is not that good, so it does not take. Still spins very well, so I don't know why. So that's an increase. If you go down here, this one will be a decrease. So if I give you, correct? If I give you an elements and you tell me which one would be higher. So we have element this and element this, element this. three elements, and you have to arrange them according to increasing electroaffinity by themselves, or electronegativity when they have in a bond, in compound. There is a bonding there. So how you have strontium, you have lipidem, molybdenum, and you have antimony. You have three elements. Antimony is Sb here. It's metalloid, and molybdenum is metal, and strontium is metal. So how you can put them in the increasing electroaffinity, electronegativity. So electronegativity, ability of an atom to pull out valence electrons from adjacent atoms within the chemical compound. Then a chemical compound, in a bonding chemical compound. Electroaffinity, it's has nothing to do with the chemical compound. Just an atom by itself has ability to take the electron from the gaseous phase, correct? So in the gaseous phase, electroaffinity always in the gaseous phase. So this one here, this is electronegativity, correct, guys? And it's the same thing with the electroaffinity. Now the radius, however, the radius here, the atomic radius, AR, radius here, by the way, radius. I'm writing with this, the mouse. So radius will be opposite. This one is decrease, and this one here increase. Quite the opposite of decrease and increase. So that's the radius. This is R, atomic radius. So are you following me here? So if I give you those three, increasing electronegativity will be what? Will be strontium is, take this one out, take this one out, take another color, green, strontium, because it goes this way, correct? That's an increase. So strontium is less than molybdenum, molybdenum less than antimony. So antimony is the highest, goes, the electronegativity goes this way here. Right, guys? Can you imagine what electronegativity is? Well, the time I think permit us to give you a scientific go, but I'm not liable. Don't do it at home, yeah, please. Don't do it. Scientific, but it has a lot of consequences. So there is a family feud. Everybody's listening. Don't do it at home. There's a family feud between the spouse, husband and his wife. Family feud. And about most of the time, maybe about life insurance. You know what I mean. Life insurance is very heavy, so quite well. I mean, over $1 million or so. And one wants to bother the other one or do damage to the other one. So the other one of them has the experience, a little bit experience of electronegativity chemistry. So what he or she did, about maybe 200, 300 toothpaste and empty all the 300 toothpaste in a big container, power container, and put it in the low heat on the stove to make it more concentrated. Everybody's following here? And then let it cool down. So took all the water inside the toothpaste out. And then when start the whole thing is, before it's cooling down, it will be like rock. So, but because took most of the water out, the H2O solvent. Refill the whole thing back again, correct? The next day, one of the spouse, I mean the innocent one, the victim one, took the toothpaste and start brushing the teeth one after the other. As soon as one brush, a tooth is the one tooth after the other. So by the time finishing the little bit, the whole teeth is, the whole thing with the gum is down. What's really happening? This is a scientific joke, but don't do it at home. That's real. That's science. What's happening? What's happening? It turns out to be inside the toothpaste is calcium fluoride. Is made to protect our teeth from the whatever leftover food, brings a lot of bacteria, correct? So this bacteria can act on the roots of our teeth, correct? So instead now you are concentrating calcium fluoride over the limit, will start eating the roots of the person who's using it, correct? So calcium fluoride, the fluorine atom, which is here, guys, the fluorine atom is one of the nightmare inside even our lab. So we don't really use it that much. Yeah, it is. It read maybe. Fluorine is the highest electronegative atom, and whoever one of the spouses start brushing his or her teeth, all the teeth will be down. So that person needs a denture. So look like 100-year-old plus looking, there's no teeth. All the teeth are out. Why? Because the concentration of the fluoride is so high. Fluorine atom, the fluoride does not like to be by itself. So whenever it's in, it will pull out all the valence electrons from from the roots of the teeth. Those are, we have carbon, correct? Mostly carbon. So it will out from the tissues all the valence electrons of carbon, nitrogen, and therefore the teeth are really missing their valence electrons that's supporting them to the tissues, the roots. So they will just drop down all the teeth. So if you get a burn with fluoride, as you get second degree burn. So it's very, very bad. So we don't really store fluoride inside the beakers or glass. What will happen? It will eat up the glass valence electrons. The glass is silicon dioxide. It has sodium cations inside, sodium chloride or sodium nitrate inside. So it pull out the whole thing, and you can see if you put concentrated fluoride inside the beaker, you will see the beaker is like a mashed potato, start dissolving itself by the fluoride solution. So the fluoride solution always put in a very hard plastic. You cannot put it inside the glass. You cannot do that. So it will be eaten up by the fluoride. So said that, don't do it at home, but that's, you can tell you, that's the highest element with 4.0 scale. The lowest one is those two here. So the metal does not like to be electronegative. The metal like to be electropositive because it gives away its electrons. But the fluorine here, they like to pull out those electrons from within the compound itself. Second one is oxygen. So oxygen is very dangerous too. It's a very highly electronegative atom as well. And you can see the third one is nitrogen and chlorine. So those are elements here, most electronegative one. When it comes to electronegativity, remember that's the ability to pull out electron within a chemical compound, within a compound. So the compound is, you have calcium fluoride, you have a fluoride here. Now the fluoride is available with interact with the organic compounds supporting the roots of the teeth. Correct? That's what it says. Yeah, that's what it says. So don't do it at home, please. So now, with the electronegativity here difference, we can determine the bond being covalent, polar. Can determine the polarity. We can determine it's polar, covalent, non-polar, or ionic. So this table here, I will say, please make you have to memorize it by the final exam. To be memorized by the final exam, because you will need it if you have the difference between electronegativity. You can calculate and you can determine if this compound or molecule is polar, covalent, non-polar, covalent, or ionic. So with this one here, with the help of this table. So you need this table as well. So let me look at this table here. So if I have, for example, here, tell me if it's polar or non-polar. I have here H, F. Is this polar or not polar? HF. So HF, the fluorine is 4.0. So 4.0, they have no units, so just scale. 4.0 minus, the H is 2.1 in the top, 2.1. So how much is this one here? So 9, this is 10, this is 9. 1.1, correct? Am I correct? So you have 1.9. You can come here, the table, your table here, and see how does it look like. So this one here. So the HF, although it's a covalent polar, but it's act like ionic because it has a value of, it should not be over 100, over 1.9, not enough. More than 1.9, not 1.8. So it's a covalent polar. It's a covalent polar. Covalent polar. Let's do another one. Let's do another one. Sodium and then chloride. Sodium is sodium, we said sodium chloride, correct? So here it is. Sodium, guys. Sodium is 0.9, 0.9, and the chloride is 3.1, 3.0. So 3.0 minus 0.9. How much, guys? 2.1. So 2.1 is greater than 1.9. So this is what? Ionic. This one is ionic. This one is compound, is ionic. So from there, you can go and look back to this one here. So you have to correct this one. This one has to be 1.9. I don't know from what, but it's not 0.8, 1.9, greater than 1.9. So if greater than 1.9, 1.9 greater than that, so it is ionic. So from this table here, we can determine with the help of electronegativity if the compound is covalent polar, non-polar, or ionic. Guys, this one here, just show you here. Ionic is close to 2, and covalent share electrons. Ionic transfer. See, that's very important here, and this is the difference between those here. The ionic are, they don't share, they transfer electron from the metal being positive, give away its valence electron, non-metal accepting this. The covalent, they share it, correct? And polar covalent, they are partial, they are covalent, but they share partial transfer of electrons. They don't transfer it 100% because of strong electronegativity, such as HF here. HF is partial transfer of, it's pulling the, so the real life should look like this. This is, I mean, the ideal, not the, so that's the, but the real life, the hydrogen field so this one partial here, negative, and this one partial is positive. Why? This electrons here resides, let's not, maybe. So the bond is shifted more towards what? Towards fluorine. So you can see in the real life that fluorine is pulling the valence electron of hydrogen towards itself. So hydrogen will like feel like I don't have any control on my valence electron because this valence is pulled like a magnet here by fluorine, by the fluorine atom. So therefore, hydrogen will be partially positive, and this is partially negative, and this is partial transfer of the electrons, correct? So this is an example here. Cesium chloride. This is ionic. Why is ionic? Cesium is 0.7 and the chloride is 3.0. The difference is 2.3. That's ionic. Hydrogen and sulfur. Okay, hydrogen is 2.1. Sulfur is 2.5. It's 0.4. So polar covalent, correct? Polar covalent, because less than 0.4, it's non-polar. Nitrogen and nitrogen is 0, covalent, non-polar. Covalent, non-polar. So you have to add non-polar to it. It's non-polar as well. So writing Lewis structure. Lewis, as you will see, had contributed in chemistry a lot. Lewis has an acid base, worked in acid base, worked mostly in valence electrons and writing the structure of a compound. Lewis called Lewis dot structure. A valence electron is recognized as a dot in Lewis structure. When you see a dot, that's electron, correct? In some designation, they write Lewis draw an arrow up or arrow down. This is different spin. This is Lewis designation for valence electrons. So The main thing in Lewis dot structure is the valence electrons. I have a compound. First, I have to know the total valence electrons of all the atoms involved inside this compound, correct? And this is here. And then before you know the total here, correct? So this is the total here. But before this, you have to put always the least electronegative inside the middle, the center. Put what? You put this one here in the center. Why? Because you can't keep those electronegative. They are pulling valence electrons. They are so aggressive. Put them what? Farther away from each other. And you cannot put them near each other. They make the molecules not stable. And that's really true. If you look at peroxide, for example, you have two oxygen neighboring each other. Guess what? This molecule is popping like crazy. You'll see making like small tiny bombs inside your labs. It's not stable. So putting the electronegative atom near each other makes the molecule not stable and makes a lot of problems. So therefore, you keep central atom always the least electronegative, and try all the time keep those electronegative, the pulling electrons, far away from each other, far away, correct? The rule number 3 is complete the octet rule for atoms except hydrogen. Well, you'll see there's some exception for that. So hydrogen has 1 electron, so it does not have octet. Octet means 8. So even with the electrons, the 8, why did they like 8? Well, they want to mimic group 8, octet 8. Group 8 is ideal gas, inert gases, the most stable of all elements. They are most stable electron configuration of all elements you can know. Then, if you have too many electrons, correct, and the octet rule is not coming, then you can make out of this a double or triple bond. Sometimes single bond will not do it, that give you a problem. So try to make double, triple bond, satisfy the octet rule. So let's look at this one here. NF3. NF3 is nitrogen trifluoride. Here, nitrogen trifluoride. Nitrogen trifluoride, and if you look, nitrogen is, I want to see if it's polar or non-polar. It's non-polar, you will see, because it's symmetrical, correct? So nitrogen, 1, 1, 1, 1, 3, then 2, it has 1 lone pair. So it is polar, it is polar. So it is polar. I'll show you how to determine later on in this chapter how the polar or non-polar from the structure, from Lewis structure. So first, which one is the least? Nitrogen is the least electronegative, correct? Fluorine is always the highest. Nitrogen the 3rd highest. So I put nitrogen in the middle here. Okay, so put the nitrogen here, guys. That's the least electronegative, correct? Least electronegative. So I put it in the center of the molecule, and then I have nitrogen has 5 valence electrons. So one here, 1 here, 1 here, and the fluorine is 7. I boxed them here. That's 7, and this is 7. All those 7. So I start making a single bond between. I start making a single bond here between nitrogen and fluorine. So this is single bond here. Here. This is a single bond. This is another single bond. This is another single bond. correct? So if you look at this, this is the Lewis dot structure of nitrogen trifluoride. And you can follow all the steps here. You can check nitrogen has 5 valence electrons and fluorine has 7. Those are the electron configuration of them here. So total of this, you have three of 7 of the fluoride. This is fluoride here. 3, 7, 21 plus 1, 26 valence electrons. You can count all those here. You'll end up having, just double check, those are 26. So 3 single bonds and one here, this one here called lone pair. Lone pair. So it has another name called non-bonding valence electron. Non-bonding valence electron. They are not involved in bonding. Non-bonding pairs or non-bonding valence electrons or lone pairs. Orphan. They are orphan. They are not a part of any bond, sharing any bond. So therefore, you can see you have nitrogen has to have 8. So how we can calculate the 8 now? Take this one out. Let's calculate the 8 for nitrogen. And for, so those are 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen octet rule is okay. Number of shared and non-shared electrons. So if you look at this, nitrogen has 8. Total of 8 shared and non-shared. One set is non-shared, correct? 2 electrons are not shared. The rest are shared. Let's look at the fluoride. We'll look at one and then the rest is the same thing. So 1, 2, 3, 4, 5, 6, 7, 8. Octet is good. So the octet, they have 8 valence electrons surrounding them, whether they are bonded or non-bonded. Does not matter. The main thing is you add them all up, they are 8. So the octet rule is held here, correct? So this is the final Lewis dot structure of nitrogen trifluoride. So now we can have this type of possibilities, formaldehyde. Of course, this one will be the best choice. But let's just look at the formal charge, how we can determine the formal charge. There is a formula here. You can follow this formula here. Write it down and write it down. The formal charge of an atom of Lewis dot structure, for example, the carbon, is the total number of valence electrons of this atom. Carbon 4 valence electron, oxygen is 6 valence electrons, and hydrogen is 1. So total of each atom by itself minus total number of non-bonding. If you have total of electrons are not bonding, then minus the total of number of bonding, correct? And then I'll show you a shortcut out of this. You will learn it very, very quick. So this is the formula it says about the total minus total of non-bonding minus half of the bonding. So let's look at this. Put this one here in, suppose we have something looking like this, correct? So carbon, okay, carbon has 4 valence electrons. Oxygen is 6. Hydrogen is 1, but because we have 2 here. Here just to determine the total is 12 electrons, correct? So what's the formal charge will appear on oxygen and the carbon or hydrogen. We can calculate any atom we want. Let's look at the carbon. Carbon, for example, the total number is here is 4 minus number of non-bonding. How many we have? We have 2 minus 2 minus half of the bonding. How many half of bonding we have? 1, those 2 sets, 2, that's 4, 5, and 6. So you have 6 minus half of the 6. So this one here is minus 3, correct? Minus 3, minus 2, minus 5, plus 4, minus 1. So carbon has minus 1. Oxygen will be 6. This is the total. Minus the non-bonding is 2. 2 from the non-bonding. And half of the bonding is 1, 2, there's 2 here set and 2 here set, 6. Those are 6. Correct? So therefore is plus 1 if we have this charge. Correct? So that's how to calculate the formal charge. Now, suppose this is very easy, but I will make it easier than for you guys. So suppose I want to draw this one without even calculation. I'll tell you what's the charge is. So let's look at this. I have here, guys, correct? 2 and 1 here. If I look at this, I have 1, correct? 2, 3, and 4, and 5, correct? So carbon is in this one here is 5, correct? I'm just getting carbon from this one here. Getting carbon here by itself. But say to yourself, the valence electrons total is 4, but appearing on it 5, correct? The total valence electron appear now. 2 towards this is for the oxygen, correct? This one hydrogen, this one by themselves. So 4 minus 5 is minus 1. Did I do this formula? No. Correct? Oxygen, let's do oxygen. So let's do oxygen. Oxygen here is connected to here, 1 here, and 2 here. Total is 6, correct? But on it, how many we have? 2 on the top, 2 on the side, correct? Connected to carbon. And this is connected to hydrogen. So oxygen has actually 5. 6 minus 1 is plus 1. Did I do all this calculation? No. Correct? So let me do another one for you. See if you can follow. Here, this example here is now when we change, but let me just do here another one. I have here fluorine, correct? I have here 1, 2, 3, 4, 5. What's the formal charge of fluorine atom? What charge will appear there? Well, total is what? Total is what? 7, correct? Total valence is 7. How much on it now? How much? 5. So 7 minus 5 is plus what? 2. So the formal charge, this one here will be 2 plus. 2 plus. Make sense? Did I do any calculation? No. Yes. The valence electron is started with the total ones, actual one. From the periodic table, number of the group is number of the valence electrons. Then you look at then the actual how many, and then you subtract whatever can be negative or positive. Correct, guys? So let's look at this now. This example here. Let's look at this example here. Now we have different ways. Correct? We put carbon here, them like this. Carbon is 2. Carbon has 1 here, hydrogen, 1 here is hydrogen. So without calculation, what will be? 4 total, correct? That's from the periodic table. That's number of the group. Minus what's actual on it? It's 4. So the formal charge is what? Is 0, correct? This is 0 here. It's correct. Oxygen, let's look at oxygen. I have 2 at the top, 2 at the bottom, and 2 at the side. Connected to a double bond. So here it is. So it will be total is 6 group. Minus the actual one. How much on it now? 6 is again is 0. Correct? That's method, my method for you without doing the calculation. Let's do the calculation together. Let's do the calculation now. So calculation, carbon. Carbon first, total is 4. So it is, total is 4. Minus, do we have do we have non-bonding lone pairs? No, we have 0. 0. There is none. Half minus half. Then the valence electrons, they are bonding. We have 2 sets here bonding, 4, 5, 6, 7, 8, minus 8. So 4 plus 4 minus 4 is 0. That's correct. Let's do oxygen. We have 6 total. That's from the periodic table, 6 group. Minus how many non-bonding? 2 sets, 4. That's the 4, 2 sets non-bonding. Minus half of the bonding. We have how many? We have 4, 2 sets of bonding here, 4. So it will be 4 minus 4 minus 2 minus 6 plus 6 is 0. So whether you do it the way of the calculation or you do it the short way, both are correct. Okay, guys. Now, the question here to you, and this is very, very important. Nature does not like bulky molecules. Big molecules, nature does not support them. They are not stable. They start, degrading themselves, decomposing themselves until they come up with smallest ratio among themselves. Nature does not like charges. So which one in the nature will be the aldehyde, formaldehyde? Somebody will go for biology. What we call this compound here? What we call this compound? You go biology. Formaldehyde. So formaldehyde mixture with the alcohol gives you what? Formalin. Did you hear anything about formalin? Formalin is used to keep dead corpse, dead body alive for many years. So they can, if you go to the biology lab, you'll see a lot of animals that are kept inside formalin. It smells a little bit bad, but yes, that's mixed with alcohol keep the bacteria out. So the bacteria is eating up the flesh and of the corpse. So keep this formalin is 30 or 40% of alcohol inside, 40% solution formaldehyde plus ethanol. So which one you think nature will support? The one with charges plus minus 1 or this? Believe it or not, this is the one favored found in nature. Nature does not like things with what? With charges. Nature does not like bulky molecules either. So therefore, this will be the best, your best choice with zero charges. That's all the time. No exception, all the time. Nature does not like molecule to be charged, does not like to see a molecule too bulky. Correct? Now, another topic here called resonance. Well, what means resonance structure? If you have a double bond through extended molecule, this double bond will migrate from one side to the molecule to the other side. And this migration of the double bond within the molecule called what? Called resonance. So, give another example here. So, let me just give you another example here. Some of you maybe go for organic. Somebody will take organic after this class. Organic? No? Okay, so anyone will take a physician assistant or physician or pharmacy, then you have to take organic. So let's look at this. This is correct. So we have here, here's double bond, here's double bond, and here's double bond. This triple bond, this benzene, this is a benzene. Because they are migrating, you cannot fix them in one position, so they migrate. So therefore, we write, okay, don't know where they are at now, those double bonds, they are migrating from one carbon to the other. So we write what? Circle here. So the benzene is written as a 6-member ring with a loop inside. This loop tells you that this three of the double bonds migrating from one carbon to the other. And that's the reason give you the stability of benzene ring. So this we call it resonance. Now, here is the same thing in a covalent bond. In the here we have the same thing here. Look at this. So the double bond can be here. If you number them 1, 2, 3. Now 1, 2, 3. Now the double bond is migrated here. This migration of the double bond from here to here called resonance. Resonance means the higher number of migration of the double bond, the more stable the compound is. Let me repeat myself. The higher number of the migration of the double bond, the higher or the more stable the compound is. So stability of the compound is related to the resonance and related to how many migration does this double bond make. So look at this. This one even 3 here. This is, say this is 1, 2. This is 3. So now this one here on the 3, correct? Now this one here, the 1. Now here, this is 2. Now the double bond on the 2. So you can see this double bond migrates through all this oxygen, to all the 3 oxygen within the carbonate ion. This is the carbonate ion, to the molecule carbonate ion, and then you see this will lead to more stability, more stability, more stability. So that's, here's the same thing. Nitrate, look at the nitrate here. Same thing we said. This is 1, correct? This is 3. This is 2. So the double bond is here between them. Here is now number 3. Here is number 2. So this is the double bond is moving around three stations or 3 places through equations. Therefore, this we can expect this one to be very, very stable anion, nitrate. Okay. So now, Lewis dot structure, as you said, it's just covalent between the covalent bonding and between the nonmetals, correct? And the octet rule means they have to have 8 surrounding molecules, but octet rule is not always the case. Not every molecule will obey the octet will have 8. Like here, boron trifluoride, here, look at this. Boron trifluoride cannot have 8. How in the world do you fit 8? You cannot fit 8. Because boron, the third group, it has only how many? It has only 3. Here it is. 3 valence electrons. You cannot fit more than that on the boron. So therefore, if you look at the boron, is 3 electrons, and fluoride ion is 7. Here's 7 multiplied by 3. So the sum of the whole electrons is 24. So you have 24 here. So you have 3 single bonds, and you don't have octet for boron. Boron has how many? Boron has 1, 2, 3, 4, 5, 6. We're always considered the octet rule for the central atom. Now for the fluorine, yes, there is octet rule. For fluorine, yes, there is an octet rule. 2 here, and 2 here, 2 here, 6, correct? And the one bonding set, 8. So fluorine is okay. Fluorine octet rule is there, but for boron, an exception. Boron does not have. And when it comes to octet rule, always the central atom. We don't consider the terminal atom, always the central atom itself. Let's look at another example here. NO. NO. You see here, the nitrogen is 5. Oxygen is 6. 11 electrons. So if you make it like this, oxygen in this hand, 2 here and 2 here, 4, 5, and 6. So oxygen is good. Octet rule is okay. However, nitrogen here, look at this. 2 and 2, that's 4, 5, 6, 7. It's missing 1 electron. So therefore, an odd electron molecule, this, like this one here, has an odd electron called free radical. What, guys? Free radical. What would call it in medicine? What we call it in medicine? Those are precursor tumors. Precursor for a tumor. So this electron here is so high energetic, can attack this by itself, can attack healthy cell and cause the healthy cell to be itself free radical, and then the whole system, the whole cells, healthy cells will be chopped down, breakage of the healthy cell to the small tiny tumors, and then spread out to all the body, then turn out to be cancer. So start tumor, start free radical, Then you have free radical reaction, turns to tumor, free radical tumor, tumor, cancer. Cancer is the last stages, the chemical reaction between free radical uh, uh, healthy cell is already turned to be free radical because attacked by see odd electron by itself. So look at the sulfur. Sulfur 6, correct? But sulfur has no octet rule. Sulfur has 12 electrons. Look at this. So if you add them up here, for this is 12. So it has 6 sets of bonding. So 6 sets are 12. So 12 valence 12. It has 6 valence electrons, but 12 electron. Those are bonding electrons. Therefore, there is no 8. So sulfur sometimes exceed the octet, and you have sometimes 12, 10, depends on the compound it's in. So let me see. Any questions so far you have? Any question you have? Any question? Well, if you don't have any question, I would feel that you know the material. So now the last topic in this chapter here, I think, or the last, still we have, is the enthalpy change required to break a particular bond. So the bond energy. So if I have a molecule, I want to break this molecule in pieces. I have to put energy inside, correct? So this is an exothermic or endothermic. If you need to put energy here from outside to break the molecule to 2 pieces, 3 pieces, or whatever the pieces are. So this is what, exo or endo? Come on, guys. You put energy in because you cannot break a molecule without putting in some required energy to break it in. So this one is what? Endothermic. And therefore, can you see here? That's an endothermic. Can you see this one here? Look at this, guys. All those are positive. Positive. Do you see negative value? No, positive. Positive. So this is, all these processes are endothermic, endo. Because you have to deliver this energy in. That's the amount of energy you have. Add into hydrogen molecule to break it into 2 hydrogen atoms, or chlorine molecule into 2 chlorine atoms, HCl into H atom and Cl atom, oxygen into 2 separate atoms of oxygen, nitrogen into 2 separated nitrogen atoms. As you can see here, those are single, correct? That will bring us to the same old stuff. Single, this is double, correct? And this is triple. So what you can see from the values, triple. So the triple is, you need to put a lot of energy to break it in small pieces. Double is moderate in between, and the single is less. So single is less. This one here is higher, correct? Because it is ionic. It acts like a partial ionic, correct? Those are non-polar, and therefore will not take that much of energy to break them out. So, and this is the conclusion here. Make sure that you understand single bond is less bond energy than double bond than triple bond. We talked about this, but just we're repeating this one again. So, average bond energy in the polyatomic atoms. Here, just an example, correct? If it's given to you, it will be given to you as in the table, or given the value will be given to you inside the final exam. The value will be given to you. So like hydrogen, H and OH, OH, H and oxygen. So I give you both So this process here, two processes here. So you look at this. So the process is two. First, you break H2O, and then second, you break the OH. So two processes, you'll have to put energies in both. So they take then the average is for the both processes are. And this is the average bond energy here when you break those bonds. Again, this one here, you don't have to memorize. If it's coming, it will come. It will come inside the exam. It has to be given to you here. So now how to calculate this one here if somebody will be given to you. If you look at this, bond energies is the total of the reactants, the bond energy of the reactants, minus the total energy of the product. That's quite the opposite of the enthalpy change. The enthalpy change is enthalpy formation of the product minus enthalpy, the sum of the reactants. Here, when it comes to bond energies, it's quite the opposite. So make sure that you understand this. This is quite the opposite of delta H when it comes to not the bond energy, when it comes to heat of the formation. So here it is delta H, the reaction. Then you have to use delta H formation of the product minus delta H formation of reactant. Okay, I'll stop here. I'll give you 1 minute, so at least quite different. We'll come back and we'll go from there. 27. So I'll stop here. Any question you have? Okay.